back to part 2. In this part we'll examine a stack's cousin, queues. A queue is a data structure that stores elements in a first-in, first-out, or FIFO manner. That is, elements are removed from the queue in the same order in which they enter. Similar to a line at a bank, customers are served in the order that they line up, thus the name. The two core operations are enqueue and dequeue. Enqueuing an element inserts it at the end of the queue, while dequeuing an element removes the element from the start of the line. Some other treatments of queues will use different terminology for these operations, such as offer and pull respectively. Here's a queue visualized horizontally. Elements are enqueued at one end, one after the other. The order of insertion is preserved in the queue. Dequeue operations remove elements from the other end so that the order that they are removed is the same. A queue has virtually the same design considerations as a stack, including whether or not we want to bound the size, what secondary functionality we provide, and how we handle edge cases. We can implement a queue similar to a stack using either a linked list or an array-based list. Let's take a look at a possible solution. I've copied the basic stack implementation we designed prior using a linked list. Let's modify it so that it supports the two queue operations. First, I'll rename the methods. Now I'll modify it so that each operation works from a different end. We could enqueue at the head or dequeue at the tail, or vice versa. Now let's test it to make sure that it works. And now it's printed in the opposite order because a queue is a first-in, first-out data structure. Note that we could use an array-based list, but if we took a naive approach, one of the operations would be inefficient, as we would have to shift the elements up or down. We can, however, solve this by keeping track of index references to the front and end of the queue, and wrapping them around every time they reach the edges. We won't cover the details here, however. Queues also have numerous applications. They are a common implementation for buffers, in which data is received and needs to be processed in the order in which it was received. Various algorithms use queues as a basic data structure, such as breadth-first search and graph algorithms. Queues can also be used to store requests or tasks for asynchronous processing. This is common in a producer-consumer pattern. The consumer-producer pattern is visualized here. On one end, independent producers generate requests for resources or to compute some task. On the other end, consumers handle tasks independently. However, since not all requests may be handled as they are made, they are stored in a queue. As consumers become available, they go back to the queue to take another task. This all happens asynchronously, so we need a queue that supports this. Typically a blocking queue is used. We don't want consumers constantly pulling the queue for tasks if there are none, continually asking for work. This sort of busy pulling wastes resources, continually asking for work when there is none. A blocking queue essentially puts each consumer, say realized as a thread, to sleep until the queue gets more work. This is a complex system. If there are too many consumers for requests, resources are being wasted. If there are too many producers, consumers cannot keep up with the demand and the queue gets full. There are several variations on both stacks and queues that have their own applications. For example, we could support the arbitrary removal of elements. This would be for situations in which a process or requests time out and are no longer relevant. The arbitrary removal of elements doesn't affect the relative ordering of the other elements, so FIFO is preserved. Similarly, we could support the ability for items to jump the line or enter the queue according to some priority. It could be as simple as a high or low priority, or we could allow multiple levels of priority. A dequeue operation would always remove the highest priority element, while an enqueue operation would insert an element in such a manner that preserves the relative priority. An efficient implementation of a priority queue is typically done with a heap data structure. We'll explore this more when we look at trees. Another variation is a deque, which is short for a double-ended queue. A deque allows you to insert and remove from both the tail and the head. This generalized implementation can be used for both stacks and queues, as well as in more general applications. For example, inserting at both ends and removing from one provides a two-level priority queue, where items can jump to the head of the line. Removing from both ends and adding to one gives you a bounded stack implementation, where the oldest items are removed from the bottom of the stack to make rooms for the new ones at the top. This is used in applications to keep track of operations that the user is allowed to undo. New operations are pushed at the top, so that the undo order of operations is preserved. Of course, an application can't keep track of every operation in memory, so the oldest operations fall out at the bottom. Both stacks and queues have very similar design considerations and implementations. Both can be efficiently implemented with either linked list or array-based lists, though some careful consideration and plenty of testing needs to be performed. As before, it's best practice to use built-in implementations, or to use a well-designed and well-tested library. Java, for example, provides a general Deques implementation that can be used as either a stack or a queue, and is very versatile in its design. As you can see from the documentation, it supports insert, remove, and peek methods from both ends with different behaviors. One set of methods throws an exception for corner cases, while the other simply returns a special value. You basically get all the variations that we've been talking about with a single interface. Moreover, there are several specific implementations, including an array-based Deques, as well as a linked list implementation. The Java Collections library supports many other variations as well, including a priority queue.